our pleasure to welcome Ton Dieker for today's SNAPP seminar. Ton is an associate professor of industrial engineering and operations research at Columbia University, and he's also a member of Columbia's Data Science Institute. His research interests lie on the interface between stochastic models and computation. Ton has received a master's from the VU University in Amsterdam and a PhD from the University of Amsterdam. And he has many honors and awards, including the Goldstein Fellowship for IBM Research, the prestigious Erlang Prize from the Informs APS Society, and the Presidential Early Career Award from the White House. Thanks so much for accepting our invitation, Ton, and the floor is yours.
Thank you, Ruba. I'm super excited to talk to you today about QPLEX, which is a modeling and computational methodology that Steve Hackman and I have been working on for several years. Let's begin with some motivating examples from student projects that Steve and I have advised. Everybody reads reports in the news that sometimes people have to wait for a long time for voting. In the picture here at the bottom of this slide, you see the voting rate as a function of time. It turns out when the doors open, it already is very busy, and also people vote at the end of the day after their work. In sports and entertainment, often people want to access the venue or concessions all at the same time. And in the picture here at the bottom, you see that this is for the arrival rate to a stadium, where there's basically one big peak. In hospitals, the arrival rate to the emergency department actually varies quite a bit over the course of a week. Here there are 7 peaks, as you can see in this picture, corresponding to the 7 days of the week. Monday is the busiest, and it's much less busy at night. So what do these projects have in common? First of all, in advance, some staffing level or equipment level has to be set. And there's a trade-off between cost and customer experience. The search space is quite large, lots of different design configurations. And on top of that, oftentimes there is what-if scenarios that need to be investigated as well. The system characteristics are quite challenging and renders many techniques inappropriate. For instance, service times are not exponential. You can see that in the data. The server capacities are not necessarily large. And as we've seen in the previous pictures, there is a highly non-stationary arrival rates, including, in fact, temporary overload. So what is needed is fast calculation of time-dependent performance metrics, such as tail probabilities for the number at the station or the virtual wait time. Here's a small selection of techniques that have been developed over the years. And each of these techniques have been developed, proposed, and applied in the context of the data and computational power that was available at the time. But painting a little bit with a broad brush here, that each of these techniques requires either Markovian, parametric, or stationary assumptions. And for our projects, again, due to these challenging system characteristics we saw earlier, this is actually problematical at best. So discrete event simulation is the go-to approach, but it has its own challenges. For instance, standard off-the-shelf software often produces time average wait time distributions or expectations, and that's misleading because you want a guarantee for each time epoch. Moreover, because you're interested in tail probabilities, you need a decent number of simulation replications, and because you need to search over a pretty large space and possibly redo this in many different scenarios, it all starts to add up. And the effort required for modeling, testing, executing, optimizing actually can be quite substantial. So QPLEX tries to get the best of both worlds. The speed of parametric formulas from the stochastic network analysis, and also some of the flexibility from discrete event simulation. And it generates transient distributions and does not rely on these restrictive assumptions. So it's inherently non-Markov, non-parametric, and non-stationary. Let's go over some numerical results. This is for the single station multi-server system. The picture here at the bottom is our abstraction of such a system. So the server pool is a vertical bar, and the waiting area is a horizontal bar. We make the standard MTGN assumptions, and we work in discrete time. Some of the notation that we use is also on this slide. Here are the details of the example we're going to work through. So there are 4 servers. The service duration is log normal, which is quite a challenge for a lot of the existing techniques. And we choose this arrival rate function, which really is a kind of caricature of all these arrival rate functions we've seen in the examples. So the peak is 5.5 times the average. Now let's look at the probability mass function as a function of time for this system. This has been generated with 1 million simulation replications. So we think of this as the truth. And I'm going to show you this movie one more time. Because in fact, there are 2 curves here. One is generated with simulation. The other one generated with QPLEX. Now let's zoom in on this a little bit more. So this is a picture of what we call the soup norm error over time. This is the maximum absolute difference between the cumulative distribution functions of QPLEX and simulation. This is also known as the Kolmogorov-Smirnov distance. And as you can see in this picture, it barely breaks a couple tenths of a percent. Now the soup norm error can be very small, but the quantiles may be very far off. So in this picture, we study the quantiles in a little bit more detail, and note that the top quantile here that you see is 99.5, and it's still spot on. Again, there are 2 curves here. Now let's look at the virtual wait time as opposed to the number in the system. So this is a picture of the cumulative distribution function instead of the probability mass function. Again, 2 curves. Here's a picture of the soup norm error as a function of time for the virtual wait time. Looks even better than the other one. And here are the percentiles. Spot on. Now we've done movies for log normal services. On the other end of the extreme is constant services. So here's a picture of the virtual wait time distribution, same setup, but for constant services. Isn't this cool? It looks like a waterfall. And again, there are 2 curves here. And I don't have to tell you that these are quite different from the common parametric distributions that we teach in our classes. Now we're going to put QPLEX through its paces. So what we do is we select 5 different service distributions, ranging all the way from coefficient of variation equals 0 to coefficient of variation equals 3. We also choose 3 different, what we call shape functions. This is for the arrival rate function, shape of the arrival rate function. We choose 6 different levels for the number of servers, and 2 different levels for the average utilization, corresponding to medium high load and high load. And because of the high arrival rate temporarily, this means that the instantaneous utilization is much, much higher than 1 in some periods of time. So if you put all this together, then the formula for the arrival rate function is shown here in the middle of this slide. And this leads to 180 experiments in our test bed. Each experiment generates 1,000 distributions because there's 1,000 epochs. So here's a histogram of these 180,000 distributions. And as you can see, the bulk of the distributions have a subnorm error less than 0.5%. And this is for the virtual wait time, very similar. Now, anybody can produce very accurate results if you put in enough computation, right? So the question is, how long does it take to generate these QPLEX results? And this is actually a function of the hardware that's used and also the implementation, of course, right? But our implementation, it takes about a second per experiment, which each of them has 1,000 distributions. So it's about less than 1 millisecond really for each distribution. And that's on a single threaded CPU. Now let's compare, because it was motivated by student projects, let's compare this to a textbook formula that a student might implement in MATLAB, as you can see at the bottom of this slide. And you see that execution time is pretty much on par. It's a factor of 4 to 5 difference. So you can think of QPLEX as a supercharged formula. Now let's go to a network with probabilistic routing. Here's the network that we look at. So this network is a variation of a network that was proposed by Kuhn back in the day, 79. There are 3 stations that receive external arrivals. There's one station that has re-entrant flow to itself. And then there's also re-entrant flow here between F and H. And the probabilities here on each of these arcs are the routing probabilities. It has 9 stations to this network. On this slide, we have further details of our experiment for this network. So the arrival rate function peak over average actually 50%. Okay. Then we set the number of servers at each of the stations based on the average effective load. So we solved the traffic equations for the average effective arrival rates. And then we use this kind of square root formula here to set the number of servers at each of the stations. And this results in a configuration where some stations are in overload for some period of time. Let's talk about the output quality. We don't have to discuss stations A and B and C because they are single stations by themselves. Here is a picture of the quality for station D. On the left, you see the subnorm error as a function of time. On the right, you see the percentiles as a function of time. This is for E, F, G, H, and I. You would think that all the errors accumulate in station I, but surprisingly, actually, it's still extremely good. And it takes less than a millisecond to produce each of these distributions. So in this section, what we've done is we highlighted that QPLEX generates transient distributions. And we've seen that it can be remarkably accurate and also is very fast. And we haven't really even begun to make it faster. In this next section, we're going to talk about an abstract modeling framework. When we show these movies to people, invariably people ask us, can you handle this system or that system, right? Everybody has their own favorite system. And when we would sit down and try to see if we can apply the same ideas, then usually we would be able to come up with something. And that led us to think, maybe there is a better way. What if it is possible to define an abstract model through input primitives. So once you specify these primitives, you have a model instance, and then derive a single algebraic equation that is suitable for efficient calculation. So this section is going to be about the first part, defining the abstract model. The next section is going to talk about the efficient calculation with a single algebraic equation. Okay, and the motivation for this is that the input primitives is something that you could specify through software. So we first go through some terminology for this abstract framework. It's a little different from what we are used to. In this picture, the circles represent entities and the clouds represent activities. Entities undertake activities for some random amount of time. So for instance, in the single station multi-server example, the activity corresponds to undergoing service. In the network with 9 stations, there's 9 activities corresponding to undergoing service at each of the stations. Labels represent an entity's status. So you can think of having numbers on top of these circles. And a key feature of what we do is that if an entity has the same label undertaking the same activity, we do not distinguish these entities. So as an example, in the single station multi-server case, the label can represent how long ago it's been since the customer started service, or how much time is left to undergo service. Or more abstractly, it can represent some kind of phase. This example with abandonment is very interesting because we have a single station, but actually in this language, we have 2 activities. The additional activity corresponds to waiting in the buffer. So these labels in the server pool and the infinite buffer, they actually have different meanings. So histogram variables are ways to encode these pictures, these cloud pictures, and it's done as follows. So for instance, in this picture on the left, you see there's 4 1s, and that's also what's encoded in this histogram here. And there's 2 4s, same thing here. Okay, so we call the vector of histograms bold H. Count vectors represent information that's not already included in the histogram that is needed for the dynamics of the system. And we denote the count variables by bold Z. So in the single station example, we can represent a state in the following way. It is not enough to know how long ago you started service. You also need to know how many customers are waiting in the queue. And one way to encode this is to say, take one count variable that represents the total number in the system, in addition to the histogram for the server pool. And if you have renewal arrivals as an example, you would have an additional count variable that represents the time since the last arrival. In this example, we have a finite inventory buffer. And as a result, some customers here can take up space in the server pool and be blocked. So in this example, you need 3 count variables in addition to the histogram, which correspond to the number in the inventory buffer, the number being blocked, and the rest of the entities. In the network of multi-server stations, the state representation has 9 count variables and 9 histogram variables. Okay, now let's talk about the primitives and how they are used to define the dynamics. We all teach this formula in our classes. How do you update the distribution of the state given the transition probabilities? For instance, for a Markov chain. Now what we do is our state is more structured. It consists of these Z variables and H variables. And what we need to do to describe these transition kernels, transition properties really is fix Z and H and define a distribution on Z prime, H prime. And we put transition properties here in quotes because I'll come back to this in a second. It need not be Markovian. So how do we construct this, these primitives? We use, the transition probabilities. We use 5 primitives, and we do this in 5 steps. So each step uses a primitive. So fix Z and H. Okay, the first thing we do is we're going to determine how many entities complete their activity for each of the activities. And we store this in a vector D. Then in the second step, we're going to choose a new count vector Z prime. The third step is to relabel the entities that did not complete, which we are going to call old. And that gives a new histogram of labels, which we call HREL. In the fourth step, we determine how many entities start their activity during this period. And finally, in the fifth step, we label these entities that start their activity during this period. And that results in another histogram, which we call H join. So the new histogram, or vector of histograms, is the sum of HREL and H join. So on the next couple of slides, we're going to go through all the details of these 5 steps. So the first step, each entity independently flips a coin to determine whether or not it completes the activity during this period. And we use gamma for that probability. So as an example, if the label represents age, then the probability of completing the activity is just the hazard function corresponding to the activity duration. And if the label represents remaining activity duration, then you leave if and only if your remaining activity duration is 1. Okay, and that together determines the vector of counts of how many entities complete their activity during this period. Now we're going to modify these 2 examples just a little bit. So if the probability mass function of the activity duration depends on the time you start your activity, then the formula gets adjusted. And actually, this is a very substantial adjustment because this is no longer a hazard function because the LM appears in the superscripts. So this kind of shows you that the gamma is the proper primitive and not the hazard function or the activity duration PMF. Okay? And this example here at the bottom is an example of a policy where we accelerate service maybe if part of the network is congested. So depending on what the count variable is, there could be some probability, or in this example, we push out people close to being finished just sooner. Okay, the second step generates the next count vector Z prime, and that itself is a primitive as a function of Z and D. We call this the routing PMF primitive. And this does not have access to the detailed label information. It only uses the counts of how many entities complete each activity, which is in this vector D. And second thing to note, this really is a global quantity. You can have entities kind of move around all over the place. Okay? And that gets stored in this primitive. Finally, the primitive also should be interpreted as broadly as routing PMF in the sense that it also incorporates external arrivals. So as an example, in our single station system, the inventory balance immediately gives us the routing PMF primitive shown here. Okay, the third step is to relabel the entities that do not complete their activity. And this is again done independently using the third primitive. So let's go through some examples. If the label represents age, then you just increase the age by 1. That's the relabeling. If the label represents the remaining activity duration, label just goes down by 1. More generally, you can think about this primitive as a transition matrix that can also depend on the current and next count vectors. Okay, and together, these new labels can be represented in histograms that we denote by HRL. In the fourth step, we use another fourth primitive, which we denote by X of Z, which represents how many entities are undertaking an activity as a function of the count vector. So, as an example, in the multi-service single station, X is the minimum of the number at the station and the number of servers. And same thing for networks. Now, how do we find the number of new entities that start their activity during this period? We look at the total that is in undertaking the activity at time t+1, and we subtract the amount that did not complete their activity, which is this quantity here. In the fifth step, we give everybody who starts their activity during this period a new label, again, independently. And that results in a collection of histograms, which we call H-join. So if the label represents age, everybody who joins just gets label 1 with probability, label 0 with probability 1. If the label represents remaining activity duration, then it is the PMF is given by the activity duration PMF. Okay, so this was a lot. Okay, 5 steps. Okay, most important part is we have 5 primitives, and these 5 primitives together define a probability, transition probability PT. Okay, so that allows us to define a map K on PMFs on Z and H. So this picture here is going to be repeated a number of times, and it shows you that you can construct new t+1 from new t through the map K, as defined here. And these news are called the QPLEX kernel iterates. You want to hold on to these news. Okay, of all the notation so far, that's important. So we just went through a single period, and if you have primitives for each period, that defines a stochastic process on the ZH. And this process need not be Markovian because the distributions of previous time epochs can be used in the primitives of subsequent time periods. And that turns out to be sometimes important. So high time for some examples. For the network with probabilistic routing, this one is actually a little bit more general in the sense that we have general routing probabilities. Okay, the 5 primitives are shown here. We already went through the first one. These 3, you can think of these as the standard ones, because as soon as you agree that you are going to keep track of the ages of everybody in service, then these 3 primitives are determined. Okay, so the remaining primitive that needs to be specified is this routing PMF primitive. So how does this look? We do this through what is known as a probabilistic program. So this is pseudocode, but with the ability to have an additional instruction, which is a sampling instruction. And all these sampling instructions are independent. So in this block here, you sample the different flows from each of these stations, going from the outside in and also exiting from each of the stations. And then this block here keeps track of some accounting, basically inventory balance. And that results in the next count vector. Okay, now what is interesting about this representation is we have introduced new variables, local variables, namely these flow variables. And I also want to say that even though it looks like this is like a simulation program, we actually don't simulate. We just use this to specify a probability mass function. Here's an example, the example with abandonment. Actually, the most important thing about this slide is that it's just one slide, because we have the whole model right here. Once we choose these activity count functions, the x's, and we agree that we choose the standard 3 primitives, then from the routing primitive, then we only need to specify the routing primitive, and that's just inventory balance. Okay, so that's the whole model. Now, we have lots of other examples that you can write down with these 5 primitives. I just want to point out that we also have infectious disease models, which is, of course, quite different from stochastic networks. And we don't quite know what the boundaries are as far as going beyond stochastic networks. But in this talk, we focus on stochastic networks. Okay, so what are the takeaways of this section? We have these 5 primitives, and they specify a model instance. Easy to specify, can handle lots of different systems. Of course, the state space is massive, right? We haven't solved that problem. So that's the task for this next section. First, the QPLEX map. The state space is massive, and this is an illustration. Even in a simple example, it's a lot. Can't do anything with it. So here, what we do is we build another layer below this picture we had earlier. This layer works with probability mass functions that are much lower dimensional. So on this level, the probability mass functions work with the ZH variables, histograms. On this level, Z and L. So instead of working with histograms, we work with labels. Okay, and there's 3 maps that you can see in this picture, and we're going to define these maps and then discuss how you get across efficiently without having to pass through the large state space. Okay, here's the formal definition of this map L. That's the one that brings you from a compressed PMF up, which is the first step. Now, there's a lot on this slide, but main thing is basically we generate these labels, IID, using this PMF mu. Mu is on Z and L, and not Z and H. Okay, so that's why the multinomial distribution appears. And I want to point out that the PZL is defined as the domain of this map. It's probably best to see an example instead of the abstract formula. Here's how this works. Suppose you have a PMF on labels, such as this one. And suppose you know that the size of these histograms, or the number of entities undertaking the activity, is 2. Then there are 6 possible histograms on those 3 labels. Okay, and of course, in general, if you have a lot more labels, the number of histograms is massive. Okay, this is just chosen so that it fits on a slide. So what we do is each of these probabilities simply becomes multinomial. Okay, that's the multinomial lift map. So what are properties of this map? First of all, this map does not touch the marginal distribution on the count vectors. And that's very important because that's one thing we might want to approximate with this methodology. Okay, and second, I want to show you or point out that this is a highly nonlinear map because the mu appears here as a second parameter in the multinomial, and therefore it's highly nonlinear. Okay, now let's talk about the map that brings us from the top layer to the bottom layer, which is the compression map. And it's shown, the formal formula is shown here. So you can think about this as a normalized expected histogram. And the domain of this map actually depends on T, even though the formula doesn't. And we denote it by PZTH. Again, let's just do an example, right? How does this work? Here is a probability mass function on histograms of size 2 on 3 labels. What we do is we first imagine that we select a histogram. Once we select a histogram, we select the label with a probability that's proportional to the frequency. So a different way of thinking about this is that the label is chosen uniformly at random. So if we want to figure out what the probability of a red label is, then we look here, we say, okay, with probability 1, the label is red if we select this histogram. With probability half, if we select this one, and probability half also here, right? So the probability would be 0.2 times 1 plus 0.3 times a half plus 0.1 times a half, which is 0.4. So the properties of this compression map are, once again, that it does not touch the marginal distribution of the count variables. Now, this map is linear, though. You can see that immediately from this formula. And it's also many to one because we have a much larger space that we compress down to a much smaller space. Okay, so what is this QPLEX map? QPLEX map is a composition. First you go up, then you go over, and then you go down. That's the definition of the map, right? But the definition of the map, of course, uses this large state space, and I'll come back to that in a second. The Q map is never going to be linear because there's a lot of nonlinearity sitting inside of this L map, even if K is linear. So you have a Markov on the top, Markov chain on the top level is not linear. Okay, so it appears like we haven't really solved any problems because we still need to investigate how do we sum out over Z and H in this expression. And on top of that, to compress, we have an additional sum. And sums over histograms, because we have so many histograms, are just impossible. Okay, so we must somehow eliminate them. And we do this by something which we call multinomial propagation. It says, instead of starting from fixed Z and H, let's start from fixed Z and multinomial H. Okay, then it turns out that as you go through the steps of the 5 steps of the sampling experiment, the multinomial property in some sense gets preserved. Although the parameters change, you can easily express the parameters in terms of the primitives. Of course, details are missing here. Just want to give you a flavor of how this works. If you work out the details, then you get an expression that looks like this. This is mu t plus 1, which is at the bottom layer, right? This is the PMF on Z and L, not the top layer ZH. Okay, that this expression here, you actually do not need to pass through the top level. You can express this as a sum that does not involve any histograms. Okay, that's the most important part on this slide. Second most important part on this slide is that each of these terms, again, if you work out the details, can be easily expressed in terms of the primitives. So I'll show you real quick. So for instance, this term here, D given Z, is binomial with a success probability that can be expressed in terms of gamma. This term basically tells you it's the probability of selecting an old entity or a new entity. So the probability is given by the total number of relabeled entities over the total number of entities. Okay, so this K prime just has 2 possible values. Finally, this is a little bit complicated. Again, just follows from the multinomial propagation. you see from Bayes' formula, you can calculate the probability that the original label is LM, given that the entity has been relabeled. Okay, and that turns out to be a weight for the relabeling primitive given here. So you condition on the original label, and then you get this expression here. Okay, again, easily expressed in terms of the primitives. So this formula really allows us to get across. Okay, I hope this is clear, without having to pass through the top, which is impossible. It's massive state space. Okay, now let's talk about the QPLEX iterates. First of all, what are they? We take these two pictures we have and we glue them together, as you can see here. Now, we changed some of the notation here because there is a clash in the notation. And the reason we do this is because this new has a lot of structure and similar to this one. But once you apply K, all the structure disappears. So the new hats are unstructured PMFs. Okay, and these QPLEX iterates are at the bottom of this picture, the mu's. They're the lower dimensional PMFs. Now, these QPLEX iterates have some optimality properties, and to investigate this, we need to define a map, which we call the multinomial projection map. So this is what basically going down and then going up. Okay, so adding this edge in this picture. Now, the name already suggests that maybe it is a projection map, and it turns out it is, onto an appropriate space, which is basically the PMFs that all have this some multinomial property. And moreover, it turns out that in some sense, the distance between an arbitrary new hat and this manifold P-mul is minimized by this K map, sorry, pi map, okay, with an appropriate notion of distance, which is the KL divergence, which actually is not a distance. Okay, so what does this mean in the context of this picture that we are developing? Well, it turns out in the single activity case, there is a bijection between the mu's and the nu's, denoted by the red arcs here. Okay, so what we can do, we can have two pictures side by side. One is for the top level, which is the one on the left, and the other one is for the bottom level. So if we start from some initial point, there's a kind of twin point on the other side. Okay, now we apply the K map. It means we leave this very structured space, okay, in general. And then we apply the projection and we come back in. Okay, and this is done optimally. So in that sense, now we have generated a new point here for the QPLEX iterates. And in that sense, the optimality is inherited. So you keep going, you have the same kind of picture going forward. It's a little bit more tricky to do this in the multi-activity case, because then you need to look at a subspace here on the right as well. But I'm not going to go into details there. Now I'm going to talk about the decomposition approach. We already saw that histograms representations are hopeless for single stations. It means even more hopeless for networks, right? And now you might think, okay, I've just seen a apparently good idea, right? To replace the histograms with labels. Well, it turns out that if you have 9 stations, that you get another curse of dimensionality, which we call the count vector curse of dimensionality, right? Even this is not enough to reduce the space. So here's the idea. We take what we call mean field approximation. So each station keeps track of its own local PMF, which we denote by mu sub m. Okay, then we need to calculate the new mu sub m from the collection of previous ones. And we define the global PMF simply by taking a product. And if you think about this, then for the Kuhn network, we need to keep track of, need to update 9 two-dimensional PMFs instead of 1 18-dimensional PMF. Okay, and that's a big, big benefit. So that's how we've generated these numerical results for the network at the beginning of this talk. So what we are doing is essentially building out this picture one more time. So now we created a kind of ladder. And on the bottom rung of this ladder, we have a collection of low-dimensional PMFs, which in this example each one corresponds to a station. Okay, we take a product, we go up, then we apply Q, which destroys all the product structure in mu t. And then we calculate the marginals, and that defines a way to get across. Okay, of course, we still need to talk about how to do this efficiently. And there are some details that are missing here, but I'll show you how this is done. So let's go back to the network example. Now we want to update, let's say, the local iterate for station H. So we have to compute mu ht plus 1 from the collection of local PMS for the previous time epoch. Well, it turns out you only need the iterates from the stations that feed H and the one for H itself. And here's the idea. The station H is a single station by itself, except for the arrivals are no longer exogenous. They are determined by the iterates of the other stations, C and F. Okay, so these determine the F sub A that goes into the iterate for the station H. Now, here are some details. I will skip maybe a lot of it. Just want to point out that this is to calculate the flow from F to H. That is a purely local calculation from the perspective of F. Okay, so it's very cheap to do. And similarly for C. And then you take the sum of the number of arrivals from each of these different flows, and that's used in the single station for H. All right. So you can also use this decomposition approach if you have grouped multiple stations together. That would also work. And I'll come back to that in a second. That's related to subsystems. All right, so what are the takeaways of this section? Is there were 2 curses of dimensionality, and we've overcome the first one by introducing the notion of compression and lifting, multinomial lifting, and the second one with the decomposition approach. And actually, what is interesting about this decomposition approach is it's actually kind of the other way around from what people have classically done, in the sense that classically people build a model and then study, do I have a product form, right? Here we do it the other way around. We say, give the modeler the power to say, let me make these stations independent, and then do the computation. So reap the computational rewards of the independence. The next section is about a generalization of the decomposition approach, which we call information structure. There's a lot to say about this, and these couple of slides really just serve as an advertisement of this topic. The motivation for this topic is that the decomposition approach imposes a lot of independence, and it might not always be appropriate to have that much, to impose that much independence for every single model you may want to build. So what we do is we replace the bottom part of this picture that we had from the decomposition by something that's more general. So we extend the decomposition approach. And the way we're going to do that is through what is known as probabilistic graphical models. So there will be graphs G and G prime, and we'll introduce lift maps, LG, and kind of compression maps or marginalization maps, IG prime. And that defines here a new map. These iotas are just like in the decomposition approach, where there were collections of PMFs, low dimensional PMFs, the same here. Okay. There's some more flexibility than compared to the decomposition approach. So let's investigate, let's talk a little bit about this map LG and the graph G in the context of an example of 3 stations in series. So the graph here is a complete graph. It has one maximal click, and that means the collection iota at the bottom layer is just a singleton. It has all the variables inside. And the map LG just picks out that element. Okay, so this is a kind of trivial example. The graph here, each station gives rise to a maximal click. And there is 3 maximal clicks of size 2. So the collection iota at the bottom of the ladder consists of 3 two-dimensional PMFs. So this is like we had in the decomposition approach. So this is the graph you would take for the decomposition approach. And the LG would, in that case, just be a product, as we've done before, using independence. If the graph has a max click that combines stations 2 and 3, then the collection at the bottom ladder will be consisting of 1 two-dimensional PMF and 1 four-dimensional PMF that needs to be iterated over. And the map LG is simply the product again. Now, this next example is a little bit more interesting. We call this the fishbone graph. This one, relative to the decomposition graph, it has 2 extra elements because there are two more maximal clicks due to the extra edges here. Okay, and so what we update, what we iterate over is actually a collection of 5 two-dimensional PMFs. And in this case, you cannot just take the product, because if you do that, you don't even get something that sums to 1. So you have to do this a little bit differently. And it turns out that the formula here at the bottom of the slide works. Okay, that produces a PMF. Now, this slide is a kind of summary of the procedure. I think I should probably skip most of it. Other than, I just want to say, we heavily use techniques that have been developed in the context of probabilistic graphical models, and also the corresponding algorithms. Okay, so some details are given on the slide, but key questions for us have been, which kind of graphs are allowed in the context of QPLEX models? And it turns out there's an interplay between the primitives and the graphs. And secondly, this is a question we don't understand much about yet, which is that there's a trade-off between accuracy and computational cost. If you add more edges in your graph, you will get more accuracy, but also it's going to be computationally more expensive. And understanding this is something, this is obviously very important, because as a modeler, you can specify this graph. Okay, this picture again glues 2 of these ladders together and introduces new maps that turn out to be projection maps onto appropriate spaces with appropriate optimality properties. Now, everything we've done so far is for this setup, this framework with these 5 primitives, right, that are specified. But actually, if you want to model machine repair, preemption, or multiclass, for instance, this framework is not flexible enough. So we actually have a much more extended version of the framework that has different primitives. So we wanted to give you a little bit of a flavor of what is needed if you want to build a different framework, what is needed what needs to be changed. And fortunately, the answer is not that much, in the sense that this picture remains the same. And the thing you have to, of course, change is on the top level, you have a different specification of your model on the large state space, right? Then at this middle level, you have to generate a multinomial propagation properties. So your primitives need to be chosen appropriately so that it enables a multinomial propagation property. Then the bottom part of this picture actually is pretty much, because we use very generic techniques, stays the same. Okay, so this section was about a graphical way to model the in the context of a QPLEX model, which allows you to basically model specific dependencies or independencies that you want in your model. This next section is about how you can potentially use QPLEX for decision analysis. And we start with the example that originally motivated this project, which is a design problem. And the details are on this slide. The most important part about this slide is that QPLEX is tailor-made for these kinds of problems because it's deterministic, highly accurate, and extremely fast to calculate. But actually, we can go much beyond these kinds of decision problems. Here's an example where an incoming customer needs to choose between 3 heterogeneous stations. And for instance, it might be possible that from the perspective of wait time, the 3rd station is preferable over the 2nd one, right? Because they're heterogeneous. So one possible class of policies is that the customer chooses the lowest sum percentile, the lowest virtual wait time among these 3. So, okay, so the sum percentile. So then the question is, to optimize this policy, either we optimize over this percentile or we even do this over time, right? Percentile over time. This example is actually quite interesting because this is an example where the routing PMF primitive is not exogenous because it uses the virtual wait time distribution, which is not known in advance. Okay, so this is quite an interesting example. Another reason why this example is interesting is because if you wanted to do simulation, then every sample path, every arrival, you need to calculate the virtual wait time distribution. And in QPLEX is a different kind of way of solving these kinds of problems. We don't have we don't have sample path as the main data structure. Now you can also use QPLEX for prediction and dynamic adjustment. So here's an example where at time t1, we are getting the information, data, the count vector zt1, and then we have an option, let's say the initial capacity levels n have been specified. Then we have the option to increase, decrease, or keep the capacity the same. So when we apply the appropriate QPLEX maps going forward, this allows us to calculate the performance metrics at time capital T and make the optimal decision. And at time 0, we may be interested in setting this initial capacity level. So what you then do is you use the knowledge that at time at time T1, you get data that allows you to change your capacity levels. Okay, so you take that into account in your decision problem. This is an example of where you have model uncertainty. So think of these arrival rate functions as having a collection of them, and you have some prior on the models. So data gets revealed over time, and then we want to use that data to update the prediction of the performance metric at time t and possibly make adjustments. So some details are on this slide. So for each model, we take the observations, the data that's available, and incorporate that in these iterates. We also then update the prior distribution with Bayes' rule, and we update our prediction with the new prior for the performance metric at time capital T. So the takeaways for this section is that we can use QPLEX potentially for all kinds of design analysis problems. So now for some summary and concluding remarks. So in this picture on the top, we talked about specifying a model through these 5 primitives. Then we had this bottom layer, this middle layer, where we worked with compressed PMFs on much lower dimensional spaces. And the bottom layer here, we worked with collections of low dimensional PMFs. And in each of these cases, we talked about computational techniques to get across without having to pass through higher dimensional spaces. And QPLEX is tailor-made is designed for transient analysis, and it has both a modeling and a computational component. Now, the takeaways on this slide, we have gone through actually all of them. So I'm just putting them up here. I just want to zoom in a little bit on this last point, which is that we're actually working towards building a prototype for a software platform based on the ideas of this talk. And also we are working on a manuscript. We hope to have both of them available sometime in 2023. And so if you're interested, please let me know and I would be happy to keep you in the loop. So thank you very much.
Thank you very much, Ton, for an excellent talk. Unfortunately, we're out of time, but maybe we have time for one question, quick question, if anyone has it.
I mean, I have a question.
Please go ahead, Nick.
Mostly just trying to make sure I have this in my head. So essentially, initially, when you introduce the 5 primitives and the distribution over histograms, essentially, there's no approximation there. Like you're exactly calculating the distribution of, say, Qs at a particular time. And the approximation comes in with the multinomial lift and the assumptions of independence across stations. Is that right?
Yeah, well, the independence across stations is the bottom layer.
Right.
And that one is not necessary. So we have this graphical model point of view that allows you to capture dependencies between stations. That's why
right.
this
That's what you were talking about in this like information section 4. So when you presented the simulation results for the queuing network with 9 stations,
that was for the decomposition approach.
Okay, so that was assuming independence, essentially.
Assuming independence. So it's very surprising, actually, that also to us that the results were so good, because a priori, I would not have guessed that you can actually do so well by an independence assumption. But it turns out that the algorithm keeps track of the distributions of departure, actually almost perfect match. So somehow that matters more than the independence, apparently. But this actually remains to be explored for the most part, yeah.
Right. So the way you kind of described the graphical element was, okay, the modeler can sort of say which things are allowed to depend on each other or specify a dependent structure.
Yeah.
And the trade-off is, maybe more accuracy, but more computational cost. But it seems like, at least in this example, you couldn't get much more accuracy, right? Like for that particular.
Yeah, it appears that at least in this example, that even if you wanted to throw more computation, it probably will not benefit you very much. But that cannot really be expected to be true for other models. So, we feel like it's a very important component of QPLEX modeling to be able to model the dependencies that you allow in your network. So maybe you would be happy to have part of the network maybe far away, model is independent from a station close by. So that's definitely something that was the motivation. Yeah. So actually, yeah, thank you for this question. It's a kind of nice summary also of everything we've done. So
thank you. Very interesting.
If there's time, I have a question.
Yeah, sure. Go ahead.
So this is also related to the sort of the dependence structures. So I guess there are 2 parts. First is when you drew this sort of graph that was not a union of cliques. you
Yeah.
had to say, okay, I'm going to use the conditional probability of blah given blah as part of that. Does it matter sort of like the way I want to say the question is, does it matter the order you traverse the graph? So you kind of start from the Z1, Z2 edge and then go out from there. Could you start from some other edge? And
Yeah, that doesn't matter.
Oh, it doesn't
Yeah,
matter.
actually,
Okay,
I didn't go through all the details, but there is an explicit factorable representation. The product structure basically is what gives you the computational benefit, right?
Yeah.
And even if you start traverse in a different way, then the scope, what is known as the scope of each of these terms, is still the same, and that's the only thing that matters for the algorithm. So
okay, cool. So
yeah.
basically, so just the graph gives you the approximate model. Basically, there's no other choices. Okay, cool.
Yeah, and there's some standard techniques that people have developed in algorithmic graph theory, where you choose some max weight spanning tree or something, and you can choose any of them, and that leads to a different representation, but it's fundamentally kind of the same product structure.
Okay.
Yeah.
And then a sort of related question is there some way in which you can think of the kind of graphical structure and the multinomial and the multinomial sort of approximation, are those both like instances of the same thing? Like the way I'm thinking of this is that we're sort of saying, in the independent case, right, you were saying each server state or each activity state is independent. Similarly, for the multinomial approximation, you were basically saying each customer's individual state was independent given the count factor. Are these two instances of the same thing?
Yeah, so in terms of this picture, for instance, it is possible to go without passing through the middle layer. That's just because we wanted to build out the picture step by step.
Yeah.
Yeah.
I mean, this makes sense, and it also makes sense that the bottom part is the same. You said it was the same no matter what your primitives are, but the top part depends on your primitives. So it makes sense to
Yeah.
Okay, great, thanks.
Thank you, Steve.
Thanks again, Todd, for an excellent seminar. And thank you all for being here. And we will see you in 2 weeks' time for another seminar by Jinwon Chen. Thank you. Good night.
Thank you all. Bye-bye.